Good too. We're looking at the 8 questions which you have to find the answers to using right-hand rules or understanding of magnetic fields. Again, the answer to question 1 is wrong. What does it say? Towards the surface of the Earth? It should be away from the surface of the Earth for the answer to question 1. But before we get to those, and I'm probably going to run through all 8 of them because I think it's that important. This should be just common knowledge now. Magnetic field lines emanate away from north poles and towards south poles when you're talking about outside of the magnet. The difference between the magnetic field on this diagram on the left and the one on the right is that the one on the right is uniform, whereas the one on the left is non-uniform. What that means is if I were to take my phone, the application on my phone, and put it here, and we never bothered to do this, but I'll see if I can remember to do it with just a bar magnet and measure how many microteslas of magnetic field strength there are there, and then I put it down here where the field lines are further apart, it's going to show a weaker magnetic field. Whereas if I had this situation, for the most part, the magnetic field in here is going to be the same. These 2 poles have to be physically quite large. They have to occupy a fair amount of space for that to be true. Because as soon as you get near the edges of the poles, what happens is that the magnetic fields start to bulge. The field lines start to bulge a bit. So they're probably even bulging near the bottom of this original diagram. But for the most part, it's pretty uniform. You need to know how to use the curly right-hand rule to find the direction of the magnetic field that encircles a conductor. You will notice that this part here has got a huge flaw in it compared to the diagram that I've given you. What's wrong with this diagram? Take a look at the one I printed out for you. There's a subtle but very important difference. Well, right, these field lines are evenly spaced here, and they're not. We know that when you get further away from the wire, the magnetic field will decrease. I just haven't had time to update that diagram in this particular file. Bottom line, your thumb goes in the direction of conventional current, which is the way that positive charge in the wire would flow. Your fingers encircle the conductor, indicating the direction of the magnetic field. You should be able to take that knowledge and transfer it into finding the pole of a solenoid. If I focus my attention on this wire that I can see at the top of the solenoid that's out in front of the solenoid, this wire here, and I take a look at the diagram and I see that that wire is connected to the negative terminal. Exactly. I have to grab the wire this way so my thumb points in the direction of conventional current, and my fingers are going to poke down into the top of it, which means the field lines go into the top, and that's the textbook definition of where a south pole is where the magnetic field lines go in. You don't need to repeat the process for the bottom. If the field lines go in there, they come out of here. Magnetic field lines around a single moving charge are still found using the curly right-hand rule. If I have this positive sphere moving towards the sky or towards the top of your paper, then I grab it. I imagine grabbing this sphere, it's like a golf ball or like a billiard ball or something, and I point my thumb in that direction towards the top of the screen. My fingers will curl around in the direction of the purple magnetic field. Now, something I didn't talk about yesterday that I'm going to talk about here today, when we find the direction of the magnetic field around this negative particle, we have to actually turn our hand over and imagine that it's positive moving in the opposite direction. Okay? I talked about that yesterday. That's not the new thing. I'm going to explain something new in a minute. So we grasp this with our thumb to the left, and our fingers will indicate the direction of the magnetic field. Okay. When it comes to the flat right-hand rule, we have force. I'll just show it to you first. For the flat right-hand rule, I'll use this one. The force on the particle is out of the palm of your hand if it's positive, and it's out of the back of your hand if it's negative. Generally speaking, everybody, with this rule, which I'm going to review, if you have a particle that's negative moving towards the sky, you point your thumb towards the sky. You don't turn your hand over and say, well, it's negative, I'm going to think of it as positive. And the reason for that is we can look at our right hand in this form and see out of the palm of your hand and out of the back of your hand. Whereas with the curly right-hand rule, if I were to use the same kind of logic, where I'm going to grab this with my thumb in the real direction, then I have to curl my fingers in the opposite direction, and that's just not physically possible. Right? But with the flat right-hand rule, you just go with the flow. Positive out of the palm, negative out of the back of your hand. With the curly one, you have to actually change the direction that your thumb is pointing. So again, from the top here, when you have a magnetic field that a charge is going to move through, the motion of that charge creates its own circular magnetic field. And it's the interaction between this purple magnetic field and the red magnetic field that produce a magnetic force between the magnets and the charged particle. But the magnets are heavy, or they're glued down, so they can't move. The bottom line is the magnetic force on this particle is out of the page, and when you determine the magnetic force direction, you don't worry about the negative or about the circular magnetic field. The only reason I put this in here at this point is to explain to you where the force comes from. But in determining the direction of that magnetic force, you don't even look at that. You just use the right-hand rule. Flat right-hand rule, and you have a slightly different diagram on the handout I gave you. I believe your handout has a hand in this orientation. Okay. It's the same thing. This is just turned the other way around. Your fingers are the magnetic field direction. Your thumb is the direction of the motion of charge. And the magnetic force is out of the palm of your hand if it's a positive charge, out of the back of your hand if it's a negative charge. And that's a motor effect. That's called the motor effect. And it may not look like it because of the way this is drawn, but this is at right angles. Right? The angle between your thumb and the magnetic field is perpendicular. So I'm just going to run through these fairly quickly. An alpha particle is traveling east through a strong magnetic field that's towards the north. Let's do a map idea here, that you're sitting at your desk and north on a map is towards the top of the page. So what I'm doing here, everybody, is I'm saying that's north on this screen. This is east. This is south. This is west. That's what I'm really doing. You're taking this whole screen off the wall and putting it down on your desk so it's horizontal as a sheet of paper. So an alpha particle is traveling east, that's this way, through a magnetic field that is north, that's this way. The palm of my hand is facing out away from the surface of the map, which means the magnetic force is away from the surface of the Earth. If you do it in real directions, and again, I really wish our room actually faced north, so north on a map would be north in real life, but it doesn't. If we're doing it in real directions, you say, well, that's north, that's east. And I want to be careful because I mix the two up when I go real directions all of a sudden. So the alpha particle is traveling east through a magnetic field that's north. It's forced out of the palm of your hand, which is away from the floor, away from the surface of the Earth. An electron is traveling west through the Earth's magnetic field. Well, the Earth's magnetic field is north. And for some reason, I automatically want to use real directions here. North is towards the back of the room. It's traveling west. West is actually that way. That's where Pigeon Lake is. And if you want to go to the sunshine province of BC, you go that way. That's west. So I look at my hand, but since it's a negative particle, it's out of the back of your hand, which is away from the surface of the Earth. If you were looking at a map, then on paper, north, south, east, west. You would be holding, and if you're watching this on video later, you don't see what I'm explaining. You would be holding your hand like this. Fingers to the north, thumb to the west, out of the back of your hand is away from the surface of the earth. Electron is traveling through space in the direction shown. What's the direction of the magnetic field right here? Well, it's either out, in, left, right, towards the top of the page, or towards the bottom of the page. But when I grasp this electron, which is negative, with my thumb in the direction that positive charge would be flowing to produce this, my fingers are going to curl in this orientation. They're going to come over the top and down in front. If they're coming out over from behind, it's going up, and in front, it's going down. That means at this point, it must be coming out. What this actually looks like, horrible color. What this actually looks like is that magnetic field orientation. And the magnetic field here is down. The magnetic field behind would be up. The magnetic field here would be in. The magnetic field here is out. So the answer is out of the plane of the paper. Number 4, the arrow shows the direction of electron flow in a solenoid. You're asked to draw a battery that would produce that. Well, if electrons are flowing this way, then they are attracted to the positive terminal of the battery and repelled away from the negative terminal. So that's the orientation of the battery. At the point in space labeled with, didn't copy. Is this the asterisk or the asterisk? Okay. At the point labeled with the asterisk, what is the direction of the magnetic field? Well, we're going to focus on this wire. We're going to grab that wire with our curly right hand with our thumb down, because our thumb has to be the direction of conventional current. And if the electrons are flowing towards the top of this wire, the electrons are flowing this way, then conventional current in this location is in the opposite direction. And my fingers are going to poke into the left-hand side. If I grabbed it this way, my fingers would be coming out of the left-hand side. So if my fingers point into this side, that means this is a south, this is a north. Magnetic field lines go into the south and out of the north. And we can answer both of these. I take it this is the spade symbol, okay, at the bottom. So for B, at the point in space labeled with the asterisk, the magnetic field is directed to the right. And the pole that's at the spade is the north pole. Electron experiences a magnetic force towards the south when traveling east through a magnetic field. We did a problem like this yesterday, but I'm going to approach it in a different way today. With this flat right-hand rule, 90% of the time you know the field and the direction of motion, and it's the force you find. But I want everybody to notice that in this right-hand rule, the three things are perpendicular to each other. What do I mean by that? I mean the force that's out of the palm of my hand, I know it's an electron, but forget about that for a second, that the force that's out of the palm of my hand is perpendicular to the field. That the field is perpendicular to the direction the object is moving. And the force is perpendicular to the direction the object is moving. We have 3 dimensions in our world, and we have 3 things. And that means that if the electron is experiencing a force south, the magnetic field cannot be north or south because it has to be perpendicular to south. If it's traveling east, then the magnetic field cannot be east or west. What I'm saying is north and south is taken, east and west is taken. The answer has to be towards the surface of the earth or away from the surface of the earth. So what you can do is just say, I'm going to say it's towards the surface of the earth and find out if it's right. If this magnetic field is towards the surface of the earth, and I'm using real directions here, and the alpha particle is traveling east, or the electron is traveling east, so I'm pointing my fingers towards the floor, I'm guessing B is down, and the electron is traveling east, it will be forced out of the back of my hand, and that's towards the south in real direction. And that's the direction of the force. So I lucked out. The magnetic field is towards the surface of the Earth. That prevents you from having to face the back of your hand south and do it that way, which for some reason is awkward. If you guess that the magnetic field is towards the sky, then you would be holding your hand this way with your fingers towards the ceiling and your thumb towards Quebec, and you would look at the back of your hand because it's an electron, and you would be saying, well, that's force north, but we want a force south, so that's wrong. 6, what's the direction of the magnetic field at that point? This is pretty much the same as another question that we just looked at, except here it's a wire. We have to grab this wire here with our thumb of our right hand pointing this way. Because that arrow in the diagram is the direction of electron flow, that means we have to switch our hand over, and the magnetic field lines do this. So at this point, P, the magnetic field is going into the paper. Seven, what do we have? A proton? Is it a proton? Okay. So that's a positive particle. It's moving in between these poles. And the magnets are the same in all 4 choices. The magnetic field is this way. So the question is, if you have a positive particle moving into the page through that magnetic field, which way is it forced? Fingers north to south. Thumb in. It's forced towards the bottom of the page. It's A. It's not forced, well, it would never be forced in the direction of the field. It's always perpendicular. It's not forced up. It's not forced to the left. It's A. And, yeah.
In that diagram, it showed a complete change in direction. Does the proton maintain?
It travels in a circle, which we will get to next week. It's going to be traveling in a circle due to a centripetal force. I kind of wanted to get rid of that diagram as soon as I saw it. That's why I flipped forward. Because it's showing like a right-hand turn, so to speak. And it would actually, the path in would probably look like this. And it would come out the back someplace. There would be a curve to it. Because as soon as the direction of the motion changes, the orientation of your right hand changes, which means the direction of the force changes. So the force is going to be continually changing direction. And it's going to result in circular motion. What do we have? A negatively charged particle moves between those 2 poles. Magnetic field is towards the bottom of the page. If you're sitting at your desk, it might become a little more awkward. You know, you might have to do this. Right? The magnetic field is north to south. The particle is traveling to the right, which is what I have. I think sometimes it might be easier, if you're sitting at your desk, to do this, to just hold the paper up. Because I think sometimes when I do this up here, it seems easier, and then at your desk, it's a contortionist kind of thing. So if you take your paper and you move it up, you're going to have to hold your hand like this against your paper, or like this. And since it's a negative particle, it's forced out of the back of your hand, which is out of the page. You guys feel a little better about this today? Okay, we'll get there. Now, what we're going to do is I'm going to run through a very, very quick review here of where we left off yesterday. So I'm looking at page 48, and I realize we did almost everything on page 48 except for the example at the bottom of the page. Am I right there? It's not 48? What's the page number? 56? Okay. So if you look at Thank you for that. If you look at page 56, am I correct in saying we completed everything except for the example at the bottom of the page? Okay. What we said yesterday, and I can go back and take a look at this. Why is it we get this magnetic force on that moving charge? The reason is when the charge is moving, it creates a magnetic field. And we learned a few days ago that the strength of that little mini magnetic field depends on a couple of things. How fast the charge is moving and what the charge is. And coincidentally enough, it's not a coincidence, those are the two properties of matter we need for magnetism, charge and motion. And what we said was that this amount of the force depends on the charge of the particle, because if the charge of the particle has more coulombs, then the magnetic field it creates will be a stronger magnetic field. It depends on the speed of the particle, because if it's moving faster, that little mini magnetic field is stronger. And it also depends on the strength of the external magnetic field. You know, and again, I regret not planning this out better, but when we had that cathode ray tube here, I was using this magnet the whole time, which is a fairly strong magnet, but it's not nearly as strong as this one. And what we could easily do, and I might set it up if I remember, I might forget though, you know me, is hold this magnet a fixed distance away from the cathode ray tube and then, you know, put a little piece of tape or a sticky or something on the screen showing where it deflects the electrons to, and then repeat the procedure with a stronger external magnet, which creates a stronger external magnetic field. At the same distance, I think it's reasonable to know that it's going to be deflected more. Right? And demonstrations are great, but we can't necessarily do a demonstration for everything. Anyway, these are the three things. These are the properties. I explained this to you yesterday. You don't have to write this down unless you want to. These are the properties needed for a magnetic force, right? Brody, what property is needed for gravitational forces? Mass. And that's it, right? So for gravitational forces, if you want to calculate the gravitational force, you take the property of matter times the gravitational field, right? What property of matter, put that away please, thank you. What property of matter, Ian, is necessary for electric forces? Charge, and charge alone, right? So that's why we have this formula that says electric force equals charge times electric field. It's the property of matter times the field that gives you the force. So force is the result of the field. Well, what property of matter is responsible for magnetic forces? Well, there's two. Charge and speed. And the magnetic field strength is given the symbol B. So that's why this formula is the way it is. There's, you know, it's not as simple as these other two. There's three quantities you multiply. But the bottom line is it's because there's an extra property of matter needed. And where that left us was with this formula. And the two examples we did yesterday did not worry about this. And the third example won't worry about it either, but the fourth will. So let's move on now. We did example 1, we did example 2. Let's take a look at example 3. A carbon ion is moving in the direction shown. I don't really care for how that's drawn. The intention is that this carbon ion is traveling into the page, and I know this may seem pedantic, which means very picky, but since that's the direction of the angle that we're seeing on the edge of the magnet, it should be drawn that way. I mean, from a three-dimensional picture standpoint, that's what it should look like. I'm just doing this up here because I believe it might be more helpful if you see it drawn properly. That's moving in. It's the artist's attempt to draw a three-dimensional picture on a piece of flat paper. Okay. It enters the region between the external magnetic poles. Can you do me a favor and use the right-hand rule to predict the direction of the magnetic force on that ion? And going along the lines of what we just talked about with one of those examples, the magnetic field is towards the left, so left-right is taken. The magnetic force cannot be left or right. The ion is traveling in, so in-out is taken. The magnetic force has to either be towards the top of the page or to the bottom of the page. And if I point the fingers of my right hand north to south, and I crank or twist my wrist so that my thumb is poking in, the palm of my hand faces the sky or the top of the page, which means the magnetic force is towards the top of the page. We weren't asked to do that, but what we're asked is, how fast does this ion have to move so that it will travel in a straight line through there? Yeah.
Since it's a carbon ion, isn't it negative?
You're told that it's positive. Are you thinking from a chemistry standpoint? Is that what you're doing? Okay. Well, a carbide ion would be negative. Carbon has, been a while, carbon has 4 valence electrons. An ion becomes an ion when an atom either gains or loses electrons to become more stable. And a stable atom has a full valence energy level. The 4 extra electrons that are in the current energy level are in an energy level that fits 8. So if we gain 4 electrons to become a negative carbide ion, it's going to be a stable ion. But we can also lose those 4 to be left with only the 2. So carbon is a unique atom where we can have positive or negative ions. This is a very weird situation because this ion, for some reason, only has a positive charge of 1 elementary charge, which means it's lost 1 electron. You have to, I don't want to just hand wave this away as if your question is unimportant, because it's a great question. You have to understand that, particularly in chemistry, it sounds like I'm going to dump on chemistry here, but in chemistry sometimes you're taught real simplistic ways of looking at atoms and molecules and those things. But the world can be more complicated. Okay? So we have to go with what's in the question. Have I answered your question? Okay. So it's a positive charge of 1.6 times 10 to the negative 19. And again, this isn't even losing 4 electrons. It's just lost 1 for some reason. So the magnetic force on this, did we say was towards the sky? Okay, good. The question is, how fast do I have to fire this carbon ion through there so it travels in a straight line? Well, if it travels in a straight line, that means it's not deflected. If it travels in a straight line, that means when it enters in this region, the magnetic force that's up and the gravitational force that's down have to balance. There has to be a net force of 0. Otherwise, there will be some deflection. So this is the magnetic force that's upwards. This is the gravitational force that's downward. Is this true, what I've just written? Why not, Carly?
Because it's not F-net? Like the F-net?
Well, F-net is 0, but that doesn't affect this statement. There's something wrong with what I've written. I just said to you, look at the diagram, I just told you the relationship between those two forces. But is this a true statement? Why not, Jack?
Because upward acceleration and downwards acceleration have to be equal, not the magnetic force, because that's left and
No. The magnetic force is towards the sky. There's no lying there. Ian?
Because there's a force going.
These are the only two forces. Those two forces aren't equal. The magnitudes are equal. And you may think it's a minor thing, but you need to write that. I don't know if you remember, but yesterday, and I'm going to flip back and show you this in a minute. Yesterday we did a problem. Does this class end at 10:40? Okay, good. Yesterday we did a problem, I believe it was example 2, where we did this. We said, let's look at example 2. What's the upward acceleration of an electron traveling in a magnetic field? And I said, well, net force is ma. Magnetic force is QVB. And I wrote this. Is that true? Yes. Because it's not two different forces that are opposite. It's just one force described in two ways. Fnet is Fm. We're allowed to say those forces are the same because it's really just one force. But when you have competing forces, you have to say the magnitudes of the forces are the same. And again, it may seem very picky, but it is important. So what we can do here is we can write QVB. That's how we calculate the magnitude of the magnetic force equals mg. And as I'm fond of saying, the physics is done. That's the physics. Now comes the math where we have to put numbers into that formula that we developed. In fact, just to pause for a second, you might be told on a university question the following. You might be told that. You might not be told any numbers. The question says, you got a carbon ion that's positive, it enters the magnetic field as shown. How fast does it have to be traveling to be undeflected? And I know that for you in high school, you go, well, what are you talking about? I can't answer that. Yeah, you can. How fast does it have to travel? Not fast. That's the answer to the question. And you're marked based on explaining the fact that there are balanced forces, and this is the answer to the question. Putting the numbers in is just what we do in high school to get numerical answers. Anyway, let's go back to reality here, where we actually know all of that stuff. There we go. So you are going to calculate, for me please, what V is. And I would, by the way, highly recommend rearranging this first. I mean, what's the alternative? Are you actually going to write down this equation on the left in green and put the numbers on paper? I suppose if it's a written response, you would need to do that. But I've tried to impress on you the idea that we're just dealing with numbers at this stage of the game. So do me a favor, take a minute and do that. If I were doing this, I would take mg, and then I would go divided by q, and then I would also go divided by the magnetic field. So I need to take 2.01 multiplied by 10 to the negative 26 times 9.81 divided by the charge. We were told what the charge of the ion is, and also divided by the magnetic field. That's pretty much the Earth's magnetic field. It's pretty weak, but we'll go with it. 6.32 times 10 to the negative 5. Got a lot of numbers there. I've had more and more students lately asking me how to turn your TI-84 into one where you can see everything. I really think that's a flaw in the TI-84 design. You type and it goes off the screen. And if you've mistyped something, you can't see it. If you're interested in getting it into this mode, I can help you out. 2.01 times 10 to the negative 26 times g. I have to divide by the charge and the magnetic field strength. So we're getting that many meters per second, or 1.9 centimeters per second. Any questions with that one? All right. I do have a demonstration that will illustrate the point for the final example, but it's not one that I want to do today. It's going to be an easier demonstration to show you when we're talking about forces on wires instead of forces on charges. I'm just checking here. Do you have some kind of weird rectangle on your diagram? Okay, that's good. What do we have here? A proton is traveling west. Sorry, a proton is traveling at 5.8 times 10 to the 4 meters per second in the direction shown. Now, this is a little bit tricky because we're used to seeing diagrams like the one in question 3 that's got an arrow at an angle that indicates in. That's not what this means. What this means is that the floor is what you're looking at. We're looking on a map. The magnetic field is directed that way, and the particle is moving this way. It's moving along the same plane as the magnetic field. It's just that it's not perpendicular. And you might have noticed that in all of the questions we've done so far, 1, the electron is traveling perpendicular to a magnetic field. 2, an electron is traveling east through a magnetic field that's south. The motion is perpendicular. 3, the carbon ion is moving in and the magnetic field is to the left, perpendicular. This is not perpendicular. When you take a look at your formula sheet, at the formula we've been dealing with, there's more to it than what I've usually been writing. What I usually just write is F equals, there it is F equals QVB. And I'm not talking about the fact that these are vector symbols. It's important that you note those things are vectors, and the absolute value sign means you're not going to get directions out of the equation. Okay? But there's that little symbol, that upside down T, and that means perpendicular to. So the velocity we use here, or the speed we use here, has to be the amount that's perpendicular to the field. And what I'm telling you is that if the field is towards the sky and the particle is moving towards the sky, there will be no magnetic force, because none of that upward velocity towards the sky is perpendicular to that field. On the other hand, if the field is towards the sky and the particle is traveling west, all of that velocity is perpendicular to that field. If the particle is traveling 1 degree away from the direction of the field, there is a tiny perpendicular component to that velocity, so it will experience a force. But as it becomes more perpendicular, that force increases. What we need to do with this example, and it's not a difficult one, is you simply need to find the perpendicular component of this velocity. Since the field is to the left, this is V perpendicular. That's all you have to do, and then you can use your QVB. It's a trigonometry problem. Sine of 50 degrees equals that perpendicular component which we need over the hypotenuse, which is the 5.8 times 10 to the 4. Did you just say Stephen Colbert? No? Yeah.
Ours says 10 to the 5.
Yours says 10 to the 5? Okay, we'll go with 10 to the 5 then. We won't want to change yours. I'll change mine up here next time. Thank you, Ian. So pretty easy math calculation here. We would take 5.8 multiplied by 10 to the 5 and multiply by the sine of 50. I was doing some work in math. I just want to make sure I'm still in degrees. So that's the speed. That's perpendicular. Now, there's something about that formula I don't like. They don't have a vector symbol above v, but it is a vector. Otherwise, how could it have a component? But that's, maybe being a little too picky. This is what we use for v. So now you're going to take QVB is the force. Q is an electron, proton. 1.6 times 10 to the negative 19 times V, which is that number we just had, 444,306. You can carry all the decimals, times the magnetic field of 8.3 times 10 to the negative 3, because it's millitesla, and we'll get our answer. How many of you feel as though you'll probably take physics next year in post-secondary? Okay. What you may discover, just for those people, and I don't want it to be a surprise, is you might be given this formula in post-secondary. And the sine theta just is a way of finding the angle. The only trick to that is the angle has to be between the direction of motion in the field. If I gave you this diagram and I said, this is 40 degrees, you can't use the 40 degrees in that formula. Do we have an answer here? What'd you get? 5.9 times 10 to the negative 16 newtons. That seems reasonable. It's a tiny force. These are tiny things. So 5.9 times 10 to the negative 16 newtons. On Tuesday, we're going to explore further applications with this in terms of competing forces. In question 3, we had balanced forces, but if I increase the speed, the magnetic force would increase, and then we could find an acceleration upwards by looking at net force. And that's where we're going with this. You have lots of time today. You have those questions. What do I say? 1 to 8 and 18 and 19. I better double check that. Give me a second. I don't want to assign a bunch of stuff that I didn't intend to. Yeah, I did reorganize it. 1 to 10. It's exactly what your handout says. Last time I taught this, I decided to reorganize this whole unit. I got to fix my notebook files. So 1 to 10. I'm not quite sure why it goes 9, 9. Does yours go 9, 9? Okay. So do 1 to 9, and then do 9 and 10.